Okay, in the name of God, the compassionate, the merciful. This is the third session on C++ template metaprogramming. This is Hussein, and we are doing a University of Bergen lecture. Our source book is what is going to be shown soon. Yes, okay. The famous 2017 book of David van der Voorde and Dog Gregor and Nikolai Justites. We have covered, I think, well, 6 chapters of that, not strictly from 1 to 6, but now we're going to cover more chapters of that. I believe that was chapter 9 and chapter 12. Yes. You guys have already received the selected parts of the book that I'm going to cover, so we can be assured that you have good sources to go through. Now, so this set of slides, they are for kind of giving you more depth in what you have already learned. So I'm going to give you some examples of using templates in practice. Now, I have to say that the book is way more fruitful than what I'm teaching you here. So it's a new to go to the book. Now, the volume of the chapter 9 is roughly the same as the previous volumes, but chapter 12 it's actually quite voluminous, so it needs more time for studying. Now I'll start with giving you what used to be the C++ compilation model, and when I say used to be, I have to say that it has changed, but not that this one has gone away. Still, if you use this technology, which you can do better nowadays, you will get better support and you will get better compilation. There are rumors that you will also get better performance. That's still not quite observed. Now, the idea is that in a C++ ecosystem, you let's say that you have a number of files that you call like F1 for file1.cpp, F2 for file2.cpp, F3 cpp, and so on and so forth. And you do your programming in each of these. You divide and conquer, by putting separate things in separate files. And these files can have references to each other. Now, before I go into the references themselves, I would like to teach you a bit of terminology here. So each of these files is called a compilation unit. Right? This is a terminology in C++. Now, let's say that in F1 you use with a syntax that we can speak about later, a function that is defined in F2. So here you just say that there is some function that is going to be available. I don't know who is going to provide that. It will eventually be provided. The compiler accepts that as it is compiling F1 CPP. Now let's say that F2, for example, so no, that one doesn't have any reference to anywhere. Let's say that F1 also has a reference to F3, and by reference I mean using material from F3. But the way that it does that is that it says that, okay, it declares that something will be available. You compiler, go figure that out later. And F3 has references to F2. So F2 is standalone. Now, when the compiler compiles each of these individual compilation units, it kind of puts holes in in those the compiled version. So compilation of each of these gives us usually, so this is roughly the model for GCC specifically. You get these O files, the object files, right? Now these are object level code, object code that are closer to the hardware, let's say. And then so once it is done with the compilation of each of these, producing the O files, then because it knows, it has the entire picture, it knows that, okay, this F thing, this F1 reference to the thing that it had left at a hold can be picked up here from F2, and this other one from F3, and this other one from F3 to F2. So it links all that, and this is what happens at the link time, right? Now, once those are linked, then you receive your executable, right? Now, in Windows, that is your .exe file. So you see, there is this model for separately compiling all the compilation units and then providing linkages between them when required. Now, this is like I said, not the most up-to-date compilation model of C++. There are modules. So if you use modules, so I'm going to write it here, C++ module. Right? If you use this one, you get more control, and you should try at some point in the future to use them. But I'm not going to cover it now. So this separation, this separate compilation, right, has benefits. So let's say that you have a header file. Now, how many of you have heard about header files before? Okay, you have. Okay, good. Now, so let's say that you have a header file in which you put a declaration. This thing is a declaration. It says that it's a promise. I am going to, at some point, give you a function called f that does not receive any parameter and returns no parameters, right? Now, and then, well, your user, so let's say that you are shipping this library called f, right? And so your user includes the header file f.hpp, and they use this function, right? But where is the definition of this? Well, when the compiler is compiling this compilation unit, what it sees is that, okay, we have a reference through the inclusion of f.hpp to this function f and a call to it. Fine, I'm going to leave that for later. I'm going to resolve that reference later. And when is that later? Well, separately, it builds, it compiles this other CPP file, which implements or provides the definition for this function f. Let's say that this is its definition, right? Now, when there is the time for linkage, this one and this one are done, right? Then it knows, the compiler knows that, okay, the f that was used here is this f that was here, right? Now, so there is a benefit in compiling these things separately. So this was this was, you know, these two can be compiled in parallel, right? There's a benefit by in doing that, because, well, when you put your declaration here and not the definition, it's if the implementation of F changes, I am not required to recompile my fmain.cpp and the same binary that was produced, the O files of you know, GCC. The O files are still in place, except for this one. You know, this very one, which is the one in which the implementation of F exists, is the only one that needs to be recompiled. All right. So that means that you will have reduced build time and reduced linkage time. All right. Now, in larger projects, that's a real benefit. And it's not just about the time, it's about, you know, people they enjoy code reuse, right? So they want to leave what they have already done intact, and they want the compiler to you know, help them do so. Now, when you get to people like me, I would rather say that I am addicted to code reuse, and so you know, I do everything I can so that I get more and more code reuse. Now, so I would like to remind you about the two-phase compilation that we talked about in the first session of C++ TMP. And so you do recall that there was a matter of producing the mold and then pouring the liquid in it so that it solidifies, and you know, you get the instantiation. So with this you know, two-phase compilation thing, it's tempting to kind of have the same model for template functions and sorry, function templates and class templates. Unfortunately, that will not work for the reason that I will explain. Now, let us suppose that we have this function called print type of. It doesn't really matter what it does, right? So the implementation is not really important. Now, this function is type parameterized, so it has a template parameter t, that is a type, and it receives. Okay, that wasn't serious.
Sorry.
No, that's okay. I you know, because I look down here, you know, I don't see your faces all the time. So it took I had some delay. No, that's fine. I had some delay in realizing what was going on, but that was fine.
All right.
Anyway, so it receives a value level parameter, which is of type t, which is its type parameter. And so we have gone for the separate compilation model. We have put the declaration here and the definition in a you know, CPP file, which, by the way, is of the same name. It doesn't need to, but it, you know, it's common when you do this kind of separation of the header and source. And so you see, you then in the source file you provide the implementation. Now, what's inside the implementation is not really important here. And then you know, in the usage site, you include the header file, and you try to use the function with, let's say, a double, right? Now, unfortunately, this will not work because, well, as you know, and probably you don't, maybe I didn't tell you this very well, this is not still a function. This is a template for a function. This is just the mode, right? Now, what that means is that it will only become a function when this type is provided, which means that this will only have an address when this T is provided, which means that when the linker makes it to here, it has done all the job for this and this and this, and it has no address for this function because we didn't instantiate print type of using double. It's only at the call site that it understands, oh, I need a double. But that's then too late, right? Because where is the double? I'm now the linker, right? I'm at a later phase of the compilation. I don't go instantiate templates. I just use the instantiated, well, I just use the available addresses so that I can link calls to addresses. So now this had been a you know long for so long, this had been a source of trouble for the C++ programmers. They tried, the standard committee tried to mitigate this with all sorts of trickeries, but then they all just failed. So nowadays, the unfortunate thing is that if you are having a type parameterization, essentially a templatized function or a class, then you have to provide all the implementation in the header, right? So unfortunately, the separate compilation doesn't work. Now, this is very unfortunate because it brings a lot of dependencies. One thing that I didn't tell you, and I should have, was that, well, why is there, right, okay, is that, see, this implementation file, the source file for the function f, it uses, well, let's say it uses cout, which is in this header, right? Now, you don't need to know exactly what cout and IOStream and all that are, but what matters is that you know that, or you notice that this header is not included in here, which means that when we perform this inclusion, right, it's that dependency on IOStream is not pumped into this file, right? Which means that this file, the object file of this, stays smaller, right? And so you get smaller code. Now, well, smaller execution. Sorry, smaller execute. What's that called? I lost my terminology. Executables. Yes, you get smaller executables. And the other thing is that when you have you know, less dependencies, if one of these changes right? Let's say that there are, these are like third-party libraries, right? If these change, you will remain immune. They won't hit you. As so this well, I should clarify who you is. When these libraries that are used in the source file get updated, the user of this F library is immune, because which means that they don't need recompilation, because they don't have any dependency on those inclusions, right? So unfortunately, that you cannot enjoy from when you have templatized libraries. So, nowadays, the very unfortunate solution to this is that you have to go for what is called header-only libraries, right? Now, in the header-only libraries, you can put both the both the declaration and the definition. Oh, sorry. And the definition, or in fact, you very well might simply decide that you just don't need any declaration, so you just drop this, because when the definition is around, the declaration is too, right? Now, okay, this is a good time for a joke. James is too tired. I hope that jokes can help him.
That's when you get the best material, though, if you're too tired.
Okay.
Well, I have one. It's fine.
Please go on.
Yeah. What do you get if you put an elephant on a piece of bread?
I don't know.
A piece of bread that's too heavy to lift.
Okay.
I see the quality of our jokes has just gradually gone down and down throughout the course.
Please. These are jokes published by Barnas Vitsebok. So, meaning the children's joke book.
Yes.
This is what entertains children.
That's very much like the whole what's black and white and red all over.
Go on.
Right. Well,
newspaper. High quality.
Nice.
Well, there's this I keep forgetting that. So there's this terminology about the junk newspaper that you get, red. What is it called? The red labels? No, what is it called? The
like the one you can you get on like transport and stuff. That's just there, kind of that.
No, it usually is like you get a lot of rumors and things about celebrities and all that.
Oh, I see. Like a
tabloid.
Oh,
tabloid. Yeah, well, but in British English there are different sorts of tabloids. So there's
Is it the Sun that we're talking about?
No, there's classification of those. I think it's red tops. Anyway, I'll look it up. But when you said, James, that what's that is like
black and white
black
and red over.
Yeah. I was thinking that. Okay, you're speaking about those, right? Okay, fine. Shall we get back to work?
Yes. Yeah. Also, Niels is ill, is what he says.
Oh, okay. I'm really sorry that two people had to go to doctor and one is ill.
Yep. Not fun.
Yeah. Sounds like doctors are in business.
Yes.
It's been a good day for them.
Making out on top.
Okay. Yeah. Right. Let's get back to work now. how many of you know what an inline function is? Okay, you don't. Okay, well, here's a quick quick demo. Let's say that I have a function int times 2. It receives an int in, and it returns 10 times 2. Right now, let me change the color. This is just too boring. Now, if you make this function inline, like if you just put inline here, right? There is that's a request to the compiler for a certain thing that I will just show. Now let's say that I see out, which is the C++ standard print. Well, let's say that I see out times 2 of 18, right? Now, usually this is a function call, which means that at this point, the compiler will go to when the flow of execution gets to this point, the compiler goes to the function times 2, and it goes then to the body of it with the substitution of n here in the body, and it works out the body, it receives the result, and it comes back to here, and it, there's a jumping between the different parts of code in the flow of execution, right? Whereas if I have an inline here, right, then chances are, and this is only chances are, that something else happened. So in that case, when I have a cout times 2 of 18, right? The compiler may, and this is just a may, compiler may just replace this call with the body. So this thing itself becomes 18 times 2 at compile time, well, provided that 18 is available. And then at the execution time, at runtime, it executes this instant. Or if 18 would have been let's say another integer called m, it's not m, right? It would have, instead of performing a function call and then returning, just inline the m times 2 here and and execute that for us. Now, why is that useful? Well, how many of you have done a module on compilers? You have, okay. No, it doesn't really matter. I'm going to explain it then. Now, so at this point, well, let me put it this way. When there is an execution going on, right? The compiler has not the compiler, the operating system gives the execution environment different tools to keep track of what it is executing and what the states of different things upon that execution are, right? Now, we're not going to get into the details of what those things are, but you see that each execution has its own settings of the things that it has to remember. Right? Now, when there is a function call like this one, right? Now, sorry, like this one. That set of, you know, working environment, it's called context. You know, that context has to change because we have to go inside this function, and the context then becomes, well, I'm now inside this function. I have now extra things. I have an argument and maybe a set of other things. And so the context kind of flows over to inside here. And when I get back to the, you know, the call site, provided that I do, when the execution gets back to the call site, it has to go back to its original context. All right. This is what is called context switch. Right. Now, context switch, for the reasons that I guess you can guess, is costly because you have to, you know, there is a stack that you have to push your context into, and then you have to perform a pop when you return.
Yeah.
You know, there's this thing called call stack, and you know, this works along that way, along that. And therefore, if you can somehow avoid getting a context switch, you have a runtime, you have better runtime, right? Now, therefore, C and C++ provide this inline keyword that you can put in front of your function declaration and definition, or definition, which tells the compiler, oh, my dear compiler, if possible, please just use the body whenever you see a call, and don't do any function calls so I don't get context switch. Right? Now, so the takeaway lesson is that you should try to do as many inlines as possible, but you have to also be warned that chances are that the compiler just ignores you, right? Because that's just a request to the compiler, and they might just choose to ignore your request.
Yeah. Do you know when they might choose to ignore it or not? You know, what's the conditions for that?
That's usually there is, if the body is too long, they will be ignored. But you know, the compilers have recently become better and better on that, but it you know, they traditionally used to be quite good with one-liners. By one-liners, I don't mean that if, you know, you put everything on one line and it does the job for you. I mean, like when there are relatively little number of statements inside the body, right? Yeah. Now, but that's not guaranteed, you know, especially because this is implementation specific, which means that each implementation of C++, you know, GCC, Clang, Visual Studio, Intel C++, all of that have their own rules for dealing with these, and there is no reason for them to have the same rules. And the thing is that, you know, there is no reason for two different versions of one implementation to work likewise, right? The standard doesn't enforce that. Okay.
Right.
Thank you for the question. Now, so let's see. So when I showed you this picture, I told you that upon the compilation of this file, my first main.cpp, because there is this inclusion, things migrate from the header file to the user.cpp, and that migration is rather a dump, which means that almost everything that is in here, and when I say almost, you know, there is a reason, but you don't need to know what's not the almost. Almost everything that is in the header file gets dumped into the user of the header file, the one that has included it, right? Now, that means that when you perform inclusion, you know, you get a bit of a code bloat, because a lot of the things that are in the header you might actually not need. Now those things in the header, if the programmer of the header file has done the due diligence, they have put as much possible into the source code of the header file, if that is possible at all. I mean, remember that with the templates, that's not all the time a choice, right? Now, some things you might be able to put in the source file that are not templates themselves, right? But the rest have to live in the header. So templates essentially are header only, right? But now, so you get to see that but even though, you know, not everything in the header file, the one that includes the header file, uses. Now that was Jan giving me your number one. Yeah. I'm surprised because I was expecting that from James.
I wasn't yawning. I was just doing this.
Yes.
You didn't yawn?
No.
Okay, well I'll delete that for now, but I'll go for a camera check in the recording.
Do that.
We need a live replay.
Yeah, yeah, that's right. Yeah, yeah. Okay. So let's see. Right, because so what I was saying was that you might get code that you're not using when you include a header file. You might get code that you're not using dumped into your source file, right? And headers can include one another, and so you there are dependencies between headers and all that, and you know, sometimes this is huge and unwanted. And so, you know, the compilers work hard to reduce this you know, inclusion model. It happens that not only is this you know, a matter of compilation time. So not only is, so let's say that you have a file, I'm going to go for the color black for the moment. So let's say that you have a file that includes let's say h1.h, and another that includes, and this is not quite syntax, but because I'm short in space, I'm doing this. h1.hpp, this one hpp2, it doesn't need to, but and then you have another file which includes I don't know, h3.hpp, and also h1, right? And then you have a source file which includes both of these. All right. Now, so the compiler, when it sees this, so let's say that we have two includes here for these two files. For these, what do I do? What do I call this one? Let's say h primed.hpp, h double primed hpp. When the compiler sees these, it goes to h1, and then it goes to h1. Sorry, it goes to h primed, and then it goes to h1, and it performs the recursion inclusion model, and it comes back, and it goes to h2, and performs the recursive inclusion model, and it comes to here because that's the second inclusion here. It goes to h3. It performs the recursive inclusion model. It comes again to here. It goes to h1. It again performs the recursive inclusion model, and you see you get these huge things that there is a lot of repetition in them, and that means increased compile time. B, because the the code is anyway being dumped into the source file, your execution time also increases. So that means that your performance will go down. Right now, with that, different projects have come to different heuristics for working against this inclusion model, or at least getting it to behave. So some projects, especially big projects, usually have what is called a pre-compiled header, right, which is like this big file which says include. Well, I have to do something. Let's say. So it says include h1.hpp, include h2.hpp, include h3.hpp, and so on and so forth. All the headers that in your project you're going to include, they're in this let's say my headers.hpp, and the only thing in this model that your source files are going to include are this, right? So if I have different source codes, they all only include this one. Now here's why, in case you haven't already noticed. The idea is that then when the compiler gets to the inclusion model, it already knows that it is done with the that was James. So you're number one, and this will be corrected if the camera checks reveal otherwise. Yes.
Oh, I confess.
Okay, well, no, not yours. Your one was
oh, right, yes, it might change to a 2.
Your number
yes,
2.
correct.
Yes.
Yeah. So let's see. So the compiler knows when it sees it here for the first time, it goes and performs the routine kind of inclusion model. When it comes to the second one, it already has a compiled version of this file, so it doesn't need to do it again. When it sees it here, it again already has it, so it doesn't need to do it again. And so that means reduced compile time, and also, because the ordering is exactly the same, reduced runtime, because the inclusion model dumps everything and it doesn't dump everything twice and thrice and so on and so forth, right? Now, usually compilers can when you perform optimization on top, they can optimize away a lot of the repetition, but the chances are that they can't. So projects have come up with these ideas that you know what, this is going to mean at least faster code and faster compilation, so let's do it. Now, like I said, the modules, the C++ modules have changed the game completely, but because a lot of, essentially the vast majority of the existing code base is still developed like this, you have to know the inclusion model of headers. Now, so let me see, can I make this bigger? I hope I can. Okay. So when you get a new project in Visual Studio, if you pay close attention, you'll notice that there is something called include. Well, there's something that reads include pch.h. That's because Visual Studio knows it's gonna do a certain number of headers, and it pre-compiles them, and it just includes that in every project that you build, just to save you some compilation and possibly runtime. Now, one thing, pre-compiled header files need not necessarily to be like routine header files that the user produces. They can very much be like compiler specific, and they can be things that are outside the reach of the user. So that means that they have access, they have the possibility of further optimization than they have for the routine headers. Okay, next joke, please. Who's gonna do that? Daniel.
I could do one.
Okay.
I was walking along the shore and I saw this giant, humongous clam, which I thought would be nice to have. So I decided to drag it with me back home. But sadly, I had to stop because I pulled a muscle.
Okay. Okay. Good one. Yeah.
I felt disgraced.
Yeah, okay. No, that was good. Right. Let's see.
The error novel.
Yes. So one thing which is very well known in C++ about templates is that they give you awful error messages. Error messages which are so long they can be considered novels. Error messages which are so cryptic that are worse than any encrypted message.
Highbrow novels.
Oh, tell me about it. Now, the good news is that C++ concepts, which are the equivalent of Haskell type classes or Idris interfaces, have improved that dramatically. The chances are high that I am not going to cover them in this module because I'm going way slower than what I had anticipated, and we need to do some practice. So I'll probably skip that, even though I would have wanted to, because you guys deserve it. But the thing is that it's without them, it's a very difficult art to actually survive out of C++ templates error messages. And I'm now going to show you one thing. Let's just oh, I need to go to Compiler Explorer. Where's Godports? Come on. Godports. Oh, yeah. Oh, it was the. Oh. Okay, and now I need to copy paste piece of code. Just one moment. Yeah, play just some commercials for yourself until I come back.
Awesome ads. Oh.
Ah, no. I don't have this ready. My apologies.
That's okay. Actually, I've been wanting to ask what the others would prefer when it comes to the exam or presentation times, because I saw the haven't answered
Right.
the doodle just yet.
Right. One thing. Thank you very much for bringing that up. I realized that I have been misleading you with my email. So the presentation will be a part of your mark. It won't be the only basis for it. You will do the coding that I promised. Okay. So
Okay.
so don't you take it wrong. And I will send in a follow-up message so that everyone is on the same page.
Daniel was asking about which time we wanted to do it.
Right. Yes. Yes. So Daniel.
Yeah. No, because I had a look at my exams and I have one on the 7th, and then possibly, though it hasn't been decided yet, the second week of December I'll have another oral exam. So I'll say from the second week onwards would be best for me, but I don't know how you guys.
Anything's fine for me. I'm done with my masters by that time, so I'm just doing this for fun.
Oh, okay.
That's very fortunate
Thank you
for you,
very
at least.
much. Thank you.
Does it have to be in person?
Well, no.
Might be a challenge.
If it is too difficult for you, we can always go with the this is something you shouldn't do, but I'm just doing it for being quick. Now, well, getting back to your question, James. So no, it doesn't need to be in person, but it would be nice. I'm coming along to Norway, and then I would be pleased to see you guys. But I don't want to give you such a hassle. You know, if it is too difficult, then
'Cause it might be difficult for me just because I head to Krakow in December.
okay. Well, is that like what is it? TFP? Is there a TFP there? Like the Lambda days? Do you go to the Lambda days?
No, my girlfriend is there.
Oh, I see.
But then it would probably be much easier if I do it remotely. If we put it back then, is my point.
Right. Right. Well, if like I said, if this is going to be like that difficult, then sure, just help us out. Yep. Now,
Oh, there we go.
so
like,
let me just walk you through this piece of code. Now, this piece of code has a map, which well, in C++ is not a function like in Haskell. It's a container, which maps, well, in this case, strings to doubles, right? Now, then what it does is that it tries to find the first empty string in the oh, not the first. Yeah, the position of the iterator to the first instance where you do an empty string here. And because this is a map, there will only one instance, if at all, right? Now, so what this is saying is that start from the beginning of this map and do that until the end of the map. What should we do until the end of the map? This is a lambda, right? What it says that find for me. So sorry. Find for well, let me read the lambda for you. The lambda takes a string by constant reference, and it only returns. Well, sorry, this is non-empty, not empty. It returns a Boolean, which checks for the string being non-empty. Okay, so that's a lambda. Now the problem is that this holds thing is not constant. Therefore, this and by the way, map another way is to think about it in terms of key value stores, right? Now, so the key, which is a string, is not constant, right? Now, that means that this function, this lambda that we have produced, is not exactly of the same type, right? Because it works with constants, right? Now, let's try to see what the error message is telling us. And this is GCC. Oh, come on. What do I do? It's not big enough. Anyways,
I think you can full screen it in the corner. Yeah.
Yeah. Okay. Now, what this is saying is that, okay, I have some header file. Well, this is a header file that we didn't include. Fair enough. Then there is another thing, which is string. Okay, there is a string in the source file. What is it about? There is this strange thing, which has an operator, a call operator, with the types being these. Well, if you don't know what lambdas, how lambdas work, you will not be able to find out that this relates to lambdas, right? Now then it says, okay, I'm confused about this find if, but you see there is a underscore underscore before the name. If you're not sure, if you're not familiar enough with how the compilers handle their own precompiled headers, you will be surprised because this is not the function that you were calling. Right? Then it says that, okay, here is another one, and then finally gets to something that you have made a call with. Sorry, made a call to. And then even though you finally make it to a function, the thing is that it's, it still has these single underline trailings, which, by the way, it just expands, but the expansion isn't that much better. It says, okay, I'm working with three iterators of pairs of const basic string and double, and there is this predicate thing which comes from lambda, right? Now, then it says, okay, the trouble is that I didn't find any match for a call to. What's that? Okay, it's a lambda. It takes a constant string by reference, sorry, a reference to a constant string. And what's this one? You see? So, yeah, and this is, by the way, the map, but fair enough. Now, okay, if you survive until then you get to see that, okay, it's not completely sure which one of these two functions it has to call. Is that this one, or is that this one? Because and I actually gave you the wrong. So you see, this is a string. This S thing is a string. This one is a const string sorry, this is a C string, which is a const char pointer, right? So what it's saying here is that should it be one that relates to string, or should it be one that relates to chars, right? And both of them need conversions. So you can't decide on which conversion you had in mind, right? So you see, this is just very cryptic, and for the trained eye, this takes time. So that's enormous. Now you can have your fun with going for Clang or other compilers, and you get your own. Oh, this one can't do the compilation because the label for the C++23 is different. I just don't recall it off the top of my head. But anyway, so we have this, which is GCC specific, and right, this one. So if you're using Clang, then you have to provide a different. The labeling is different. I think it's slash CPP C++. Well, anyway, doesn't really matter. So now the point is that you can have your own fun with this, so that you come to understand that the error message that it spews is just huge, and it's it takes a lot of time to train your eyes with these error messages, even with the coloration and all that. And even though sometimes it's still very cryptic, so it happens to me also, but a lot of the times that it takes me like maybe an hour or so to just go through the error message that I receive and decrypt it. It's unfortunate about the C++ templates that they are that way. Like I said, concepts help that a lot. Let's get back to the slides. Okay. Now we have 20 minutes left, and I'm only through to chapter 12. This is only like half of the material. We need to cut it sometime in the middle. Let's see. Is anyone too tired at this point because of the class, not because of what happened last night?
Nope.
No? Okay. All right, then we'll march on. So I have thus far shown you a number of times instances of template classes, sorry, class templates and function templates, right? Which are essentially templatized by a type name, sorry, by a type or by a non-type, right? Now, I don't recall whether I gave you instances also of I think I did give you these, right, which are called alias templates, right? Now these what this is saying is that when I write data list of T, I mean data of T pointer. So I'm just giving myself some shorthand, you know. Now I think I didn't give you, I mean, I'm confident I didn't give you one of these or one of these, right? So I'm gonna go through them. So what this is saying is that, okay, 0, so if I just say 0 of int, right, I will get a 0 which is of type int, because you know 0 itself, well, I go through that, because 0 itself has no type, right? So well, no, not that it doesn't have a type. It has a default type, but it can be of many types, right? Now, if I want specifically the 0 of integers, this is one way of doing that. Now, you understand that that gives me a value of a specific type stored in a variable, right? Now, that value, in order to obtain that, we have to get past, we have to pass a type, right? So that's why it is called a variable template, right? That thing itself, so 0, this thing itself isn't quite a variable in the sense that log isn't quite a variable, sorry, a function. 0 will only become a variable when we pass the type parameter, right? So in the same way that log will only become a function as soon as we pass it as an argument, right? Now, so that was the case of the type of the variable depending on this template parameter, but that's not necessarily the case. So for example, here, the type of that variable is not dependent on the template parameter. Both are accepted, right? These are both variable templates. Now, these are only available from C++ 14 onwards, but I imagine that you guys will never, no, not never. The likelihood is little that you have to touch code at this stage that comes from before C++ 14. But just in case you need to work with legacy code, which is not very unlikely in the future, you should know this. Now, so what I showed you in this example, these are what is called, these are all kind of namespace scope, which means that they're not inside a scope that is smaller than a namespace, but they can. So here, for example, we have a class that's called list, and inside that list thing, there is another class. So we have a nested class that itself is template parameterized. Inside it, we have a constructor for list. Remember that constructors of classes in C++ are the functions that have the same names as the class name, right? Now we have a constructor, which is a function, which is a special function, which is templatized. These two are the, this is the class template, this is the function template, right? And we can also have like member variables. So for example, here we have a static data member, which is a member variable, right? Now, if you want to implement these outside the class, there is an extra indirection involved with the syntax. So let's say that we are outside list and we are about to implement handle. Right now, first of all, list of t, because it's outside the class, it has to be list of t. Where does t come from? Well, it comes from upstairs and here, right? But well, handle itself also needs a type parameter. Unfortunately, you cannot put that next to this, because that would be a template parameter for list. So what you need to do is that you need to have a second template parameter declaration that relates to the ones, that is the ones that relate to handle, right? So yeah, syntactic boilerplate, what C++ loves, unfortunately. Actually, they don't love this, but these things are so coincidental that, and they are working on making it easier, but they're still far away. Now, so how many of you know what a virtual function is? Okay. No problem. Let's say that I have a dot D and a dropped D, which inherits publicly from B. Recall that this is the syntax for public inheritance. Okay. Now you know that I can say that, let's say the pointer P equals new D, right? And I can perform calls on this instance. So let's say that it has BP has a member function MF that takes no parameters. So I can perform this call, right? Now, let me put something here. No, let me just void. Come on. And let's say that this guy also has an MF of itself. Right. Now, if that is so, then when this function is provided here and here, upon this call on line star, right, the call is actually to this one rather than this one, because BP is a pointer to base, to B, not a pointer to D, right? Whereas if I add the keyword virtual here, then the call on line star would be a call to this one, even though BP is a pointer to B. Because even though this is the static type of BP, the dynamic type of it is a pointer to D. So this means that it's a pointer to D. And when we mark a function, a member function as virtual, we are asking the compiler to bind calls according to the dynamic types. Now, the compiler does that using what is classically referred to as virtual tables or V tables, right? Which says, okay, it's this table that says, okay, let's say that the function MF that has entries for B and for D, and let's say that there are other functions that drive. So it knows, so when there is a call to a virtual function, it goes to this vtable thing, and it has the dynamic type of BP. It tries to go through these entries here and find out which one it is that the dynamic type matches. It gets to here and says, aha, I know. So that has to be a call to this one instead of this one. Right? Now it's a good practice to also put virtual here, although that's optional, because if it happens that you have forgotten to make this one virtual, the one in B, then the compiler tells you, did you mean to make that one also virtual? Right? But you know that's just a warning, because very well you might want to make this virtual for the classes that drive from D. Right? Now anyway, so okay, that's about the virtual functions. I'm gonna roll these. Oh. Daniel, you were taking notes. I'm sorry.
No, that's okay. I was wondering if there's any like benefit to virtual functions.
Right.
Functions.
Very good. Very good. So the benefit is in what is called polymorphism, which means that you can write one code which works for the base class,
Yeah.
and then have as many derived classes as you'd like, and that same single code works for all of these, right? So and this is what is called dynamic polymorphism. I'm going to get into that, right?
Okay.
Let's see. Now, unfortunately, templatized member functions cannot be virtual. And I'm going to ask Jan about the reason why he thinks this is the case.
Hmm. 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 Hmm.
Would you be interested in a hint?
Certainly.
Okay. When you templatize a function, it's not exactly a function any longer. It's
Compile. It's sort of a promise, isn't it? No, well, not in the technical sense, but
Mold.
it's a mold,
it's a mold.
right?
Yeah, yeah.
Okay. It's not still a function.
Hmm.
It will become a function
Hmm.
sometime in the future,
Hmm.
right?
Whilst the virtual
So-
function is given as a function.
Yes. So it has in the V
The-
table, there are addresses
Hmm.
for the
In the
function.
V table. Yeah, yeah.
Yes, right? Now that means that a templatized member function cannot be virtual because there still is no address available.
Hmm.
They will only have addresses as soon as their templates are given arguments to,
Right, right.
right? So that's why
So
they
there's a
cannot
clash there.
be.
Yeah, makes sense.
Thank you. Um,
Thank you to Daniel. Hmm.
yes, thank you, Danny. So this is a good place to actually stop. We have still, I think, 13. Yeah, 13 slides.
To get
Okay.
going.
You know what? In the practice session,
Hmm.
I will not
Yeah.
continue teaching these. I will leave these for next week.
We can have a read of them, can we?
You can, and you can also
The
read
book
through
will
the
have it, of
chapter.
course. Yeah.
Yes, you can also read through the chapter, which would be more beneficial than just looking into my slides. But it's you know, it's due on me. I have to still teach you the material. So let me just stop the share and also stop the recording.